Well, this is a very interesting and deep and topical question.
If I put my hand in front of the beam at the Large Hadron Collider, what would happen to my hand?
Don't know.
Not a good idea. Wouldn't recommend it. And in fact, of course, you can't. The beam is 100 meters underground.
Well, I really don't know. I mean, you've got these things coming together and you would have thought it'd be extremely dangerous. Somebody would yank you out of there before you could do that.
I don't think you'd feel very much.
That's a good question. I don't know, is the answer. Probably be very bad for you. And they'd be very cross with you, as well, all I can say.
I don't know the total amount of energy that would be distributed, and I don't know the energy density.
The beam is sending protons in one direction, and of course there's a counter beam going in the other direction. These protons have an energy of order, when it's reached its maximum of order, of 7 tera electron volts. That's about the energy of a mosquito, so it's not a lot, right? It's of one proton. But the difference is this energy is like concentrated into a volume a million times smaller than the mosquito. So it's like a really sharp pinprick, but it's still only one proton. Unfortunately, there are something like 3,000 bunches going around the beam, around the accelerator. Each bunch has 100 billion protons.
But by the scale of energies that we notice, it wouldn't be that noticeable. It'd be interesting. Would I put my hand in the beam? I'm not sure about that.
Because the other thing, because I've worked at synchrotrons, and the real problem with if you're getting off synchrotron radiation, because you've got particles travelling very close to the speed of light, if they're accelerated, then you're getting off synchrotron radiation, and synchrotron radiation is very nasty.
When they collide them together, there are something like 600 million collisions per second. So there's a lot of collisions go on. The total energy stored in the beam, whereas the energy in an individual proton may not be very high, the total energy stored in that beam is about 300 megajoules. That's like the energy of an aircraft carrier moving at 11 knots. So now that beam's going to come round, it's suddenly going to hit your hand or your body, whatever you've put in, and it's got to deposit that energy. So it's like being hit by a massive object, and I don't think you'll survive very much.
But because it's just hitting such a small space, won't it just drill the ultimate hole through your hand? Why would it start affecting other parts of your body?
That's why I was hesitating, of course, at the beginning, because I don't really know what will happen. When they collide, the beam has ranges from a width of about 1 millimeter down to a width of about, I think, like a fifth of a hair's width when they actually collide the beam. So they're really narrow when they collide them. When they're not being collided, they're about 1 millimeter. So they're going to come in and crash in here. So I have thought maybe they'll just shoot through, but it seems to me that what's got to happen is this energy has all got to be dumped because it's now hitting a lot of matter. Normally it doesn't hit anything. It's almost a total vacuum in those things, in the accelerator ring. But now there's this big high density region. And so all these particles, it seems to me, will just hit in there and just start bombing out. So that's why I thought it might be a bit more dramatic than a little pinprick going straight through you.
There's a vacuum there, so that might have some unpleasant consequences on my hand, pressure change. But I don't think it would have a huge effect.
If there was a galaxy made completely out of antiparticles, would it behave the same way as ours?
So the main thing that goes on in galaxies is gravitational, right? And gravity doesn't care whether you're a particle or an antiparticle. Gravity cares about the fact you've got a mass. And so as far as gravity is concerned, as far as forming this anti-galaxy, if you like, I think that dynamics would be the same. With regard to the actual interactions, assuming that the anti-hydrogen can form, for example, so an anti-electron and an anti-proton, then I suppose the same basic processes can take place. They will emit light when they interact with one another because the light is just an emission of energy. And as long as that's still taking place and energy is being lost, then you'll still have light.
The reason we know the universe doesn't have such galaxies in it is that actually even the empty space between galaxies isn't completely empty. And so this galaxy would actually start interacting with its neighbours. And of course, when the matter comes into contact with the antimatter, it would annihilate. There'd be a big burst of gamma rays. And the fact that we don't see a very large gamma ray background in the entire universe tells us that the universe isn't actually full of antimatter galaxies as well as matter galaxies.
At the point when the universe came into existence, so did all the forces and physical constants, which affect the universe today. However, if the universe was to come into existence again, like another Big Bang, would we have all the same forces and the same physical constants?
Oh, okay. So this is the sort of multiverse idea, and the fact that we could have a wide range of different universes with different physical constants.
Oh, that's a good question.
That's a difficult question to answer because, of course, you can't do the experiment. You know, what physicists like to do is do an experiment, and we're not allowed to make universes, or at least we haven't figured out how to do it yet.
The idea now is that little bubble universes can pop up everywhere, and it's thought that right in the early stages, the fundamental constants can be different. And the question then arises, what would it be like living in a universe where the fundamental constants were different, where the mass of the electron was different, or its charge or Planck's constant were different, and so on. And this is a fascinating question.
So it's not clear. There are theories that actually say that the universe didn't come into being as a single universe, that actually lots and lots of universes were created, a thing called the multiverse. And in some of them, the laws of physics work, and some of them they don't. And so the ones where the laws of physics work kind of thrive and take over. And so it could be that there may be other universes out there that have very different laws of physics, different values for physical constants and so on. So but it's a sort of, again, it's sort of on the realms of philosophy rather than physics, because it's not something you can really do an experiment to test.
Will we get the same forces of physical? Now that's really beyond anybody's imagination.
I think that the current understanding is, in terms of a multiverse situation at least, that there could be other universes with radically different physical constants.
I mean, Dirac said that God thought that God created the universe with beautiful mathematics. And you're asking the question, if he does it again, or she does it again, is it going to be the same mathematics, or is he going to twist it around in some way? So I really don't know the answer to that question. I don't know that you could ever begin to answer that question.
What we can't explain, even within the context of string theory at the moment, is the relative magnitude of those forces. We still don't know why gravity is so weak compared, say, to electromagnetism. We can measure it, and we can understand it in terms of the constants, but we can't predict those constants. The electric charge, why it's got the value it has, the masses of the particles, why they have the values they have. So until we can do that and definitively say this comes from, this is a unique solution that can have no other values, then you can't say that if in a parallel universe it suddenly popped up, the universe popped up in that you would have all the same couplings.
But it turns out that we have to be very careful about how many of these constants that we could imagine turning around, because there are certain scenarios that if the constants were very much different from what they are, we wouldn't be around to observe it. I mean, so certain values of the constants are just not conducive to life, and certainly not to intelligent life. So, for example, gravity has to be extremely, extremely weak.
What would happen to the Earth if one of the closer stars, like Alpha Centauri is the example we were given, went supernova? Would the Earth be protected by its magnetic field?
Alpha Centauri won't go supernova. If a close star went supernova, then there would be radiation coming at all wavelengths. But it turns out our atmosphere does a very good job of deflecting that radiation. I mean, radiation comes from the sun all the time, but we're not affected by X-rays, for instance.
Well, this is a common doomsday scenario, right? Supernovae explosions are some of the biggest, most catastrophic events that we know of in the universe. So it's very reasonable to say what would happen if one happened nearby. We know that the sun will not go supernova. It's not the right type of star. It's not massive enough to go supernova. But maybe there are some stars in our neighborhood that might. We actually know that of the type of stars that are likely to end their lives in a supernovae, there aren't that many that are that nearby. So for something called a type 2 supernovae, which is when a star just gets really massive and blows itself up, one of the nearest candidates for that is actually the star Betelgeuse. It's a famous word, and it's also a famous star. It's actually the shoulder of Orion, one of the well-known constellations. It's very red, and we know that it's actually probably nearing the end of its life. Maybe not on the timescale of humans watching it, but it could be thousands, it could be just millions of years away.
Still, the main damage, we wouldn't get very much optical damage other than looking at it. So if a star supernovas, it'll get very bright, and it could affect our eyes, just as when you look at the sun, it will affect our eyes.
But even then, Betelgeuse, which is about 400 light years away, it's still too far away, luckily, to probably cause us enough damage. If it went, it would be quite spectacular. We would probably see it with the naked eye in the daytime. That would be the visible light output. We'd have to worry about something like gamma ray radiation, but even then, it's probably too far away, thankfully, to do much damage.
Do you have a favourite symbol and why?
Ah, my favourite symbol. I don't know if we've done the favourite one yet. My favourite symbol at the moment is probably lambda, the cosmological constant, because it's this enigmatic quantity which could actually be driving the acceleration of the universe today, and no one knows why it's got the value it has. We should do a video on it.
Oh, the fine structure constant alpha, 1/137.0599. It's my favourite. Look at our 60 symbols video on it, on alpha.
I quite like the symbol for infinity because it's a cool concept. It's a really hard thing to get your head around, but also it's just a nice symbol, and it kind of packages up what it means. You know, you've got this infinite loop that just keeps going round and round and round, so it kind of does what it says on the tin.
I guess my favourite symbol is a slightly unusual one, which is a symbol called upsilon. Greek letter, looks like a seagull, and it's used by astronomers to measure the mass to light ratio of things, how much mass there is and how much light there is.
And you've discussed it on 60 symbols.
And we made a video, and it's not one of the most popular ones, I'm sad to relate, yes.
I think my favourite symbol is the infinity symbol. I really like the concept of infinity, even though I think about it a lot. It just blows my mind every time. And I just like the little infinity. It can just kind of go on forever.
So I guess aesthetically, or in terms of the background of the symbol, that's what the symbol actually means. I guess those are two separate questions. Aesthetically, either psi, pitchfork one, or big sigma, which is sort of this sort of, looks to me almost like a strange sort of Pac-Man type thing. In terms of what the symbol means and relates to my work, I guess it's got to be Planck's constant, largely because Planck's constant is fundamentally embedded in quantum mechanics, the study of small things.
Well, I've thought about this, and I will go for a ket. No, for a bra, because Dirac invented this wonderful notation. There's something like that which he called a bra, and something like that which he called a ket, and the two together made a bracket. And he was really proud of it, because this word bra is in the English dictionary. It is an actual word in English, and he invented it. And he's proud of it. He was proud of it because he was in the dictionary, not realising that it had other connotations.